So I have 40 of you joining. All right. So two plane mirrors are inclined at an angle theta. So these are the two plane mirrors. So M1, M2, M1 here, M2 here. The angle between the two mirrors, we are told, is theta. A ray of light, which is parallel to M1, first incident on M2. And this ray, after going through two successive reflections, when you are drawing, please, your parallel line must be properly drawn. Okay. So this ray, after going through two successive reflections, so one reflection becomes parallel to M2. After the ray goes through two successive reflections, it becomes parallel to M2. Now, the task is to determine the angle between the mirrors. So this is the incident. With its interaction with mirror 2, this is the reflection. And then upon incidenting on mirror 1, this is also the reflection. So it is going through two reflections. Frank.
Sir, please, in the question you gave us, the inclined mirror was mirror 2. And
Don't worry. It can be both, but I can still change it to as how you are saying it, okay? Okay. So our task is to determine the angle between the mirrors. We solve this using the laws of reflection. This is ray 1. Ray 1. This is ray 2. Ray 1, this is the incident. So meaning that this is the point of incidence. This is the point of incidence. And normal at the point of incidence. So this is N1. Angle of incidence. So I1 is equal to angle of reflection I1. So yes, that is angle of reflection is R, but the rule of the game says that angle of incidence is equal to angle of reflection. So if incidence is I1, reflection would also be I1. To mirror 2, this becomes a point of incidence. And so a normal from it would also give us this. This is N2. So the angle between N2 and that. Frank, don't worry. Frank, don't worry. This is I2. And this is also I2, since angle of incidence is equal to angle of reflection. Now mirror ray 2 is parallel to M2. And note that parallel lines have the same slope. So if the angle between M2 and M1, mirror 2 and mirror 1 is theta, the angle between ray 2 and mirror 1, which is parallel to M2, would also be theta. So this is theta. By alternating angle rule, this is also theta. This is also theta. The angle between the normal and the mirror must sum up to 90. So this angle here must be 90 minus I1. Please mute yourself if you haven't muted, okay? Then this other angle here would also be 90 minus I2. So let's label these triangles here. If we have O, A, B, C, when we consider triangle O, A, C, we have theta plus 90 minus I1 plus 90 minus I2, summing up to 180 degrees. And here I'm using sum of angles in a triangle OAC. Okay, so we have theta plus 180 minus I1 minus I2 equal to 180 degrees. When we send 180 to the other side, we have theta minus this is equal to 0. 180 minus 180. When I send 180 to the right-hand side of the equation. Therefore, we have theta giving us I1 plus I2 for the chosen triangle OAC. So this is one equation we have. Then choose the other equation, the other triangle. When we consider triangle ABC, sum of angles in a triangle. We are basically using the laws of reflection in solving this, okay? So let's sum up the angles in triangle ABC. We have 2I1, meaning the angle at C, plus 2I2, the angle at A, plus theta, also summing up to 180 degrees. Therefore, when we pull out, this is also giving us 2 out. I'm coming. When we factorize 2 out, we have 2 out, I1 plus I2 plus theta. Oh, sorry. And I've already written the indicated theta. Okay. So theta plus 2 times whatever is in bracket is equal to 180. This is equation 2. And from equation 1, we derive that theta is equal to I1 plus I2. So wherever I see I1 plus I2, I substitute theta. So we have theta plus 2 times theta is equal to 180 degrees. Therefore, 3 times theta is equal to 180. When we divide through by 3, the angle between the mirrors is equal to 60 degrees. Ladies and gentlemen, this is the solution to the problem. So you conclude, therefore, angle between mirror 1 and mirror 2 is 60 degrees. Hey, Junior, Saki.
So please, if you used another way of doing it, like the angle theta at where C is, when in the loss of effect, that place is equal to the 90 minus I1.
Yes, that's also correct. I get you. You see, because M2 is parallel to rail 2, I can also say that if the angle between the mirrors is theta, this is also theta, and so this will also be theta. Okay, there you can also use that as well. But I am using this because we just want to apply the laws of reflection. But you can also use parallel lines approach to find that. All right, please, is there any question? Is there any other question? Okay, please give me a minute to take attendance and then drop it in the group. So just a minute, I'll be back. I sent another question. I'll leave that to you. Please do it. Some of you made time to do it, and so the solutions were sent to me. Okay, please, we have discussed this one, so I want you to use the same method in analyzing that particular question. Okay, at least use your experience here to quickly answer it and then get back to me. Just use the same laws of reflection, and you'll be able to prove that. Janelle. Hello, Janelle. I'll be expecting your solution. Okay.
Yes, please.
Frank.
Please, should we do it now or after class?
After class, we'll be doing spherical mirror, so we'll do it after class and then get back to me. All right, so please, are you done copying? I'm moving on to a new page. Okay. So we go to curved or spherical mirrors. We have two main types of curved or spherical mirrors. We have concave mirror and concave or converging mirror, and we have convex or divergent. Curved mirrors or spherical mirrors are just part of the spherical ball. Okay, so it's part of a ball, a ball whose shape looks like a sphere. So when part of it is taken and shaded, we form the mirror. So assuming this is that spherical ball in question, if we decide to take section of this, a section of this, maybe a section AB, and if I decide to shade or coat one end, and here I'm shading or coating the outer part with silver, meaning this is the coated parts, and then the inner part is the reflecting surface. By this, I have formed a concave mirror. So a concave mirror is such that the outer part is coated, and then the reflecting surface curves inwardly. So where we are indicating with the ciliated lines, the lines at the back represent the coated end. So this is the coated. And this is where the arrow points to, is a reflecting surface which curves inwardly. So for a concave mirror, this is it. Now the same spherical ball, if I decide to choose a section, and this section, I'm deciding to coat the inner. So this time around, the inner part is coated. That is the coated part. And then the reflecting surface, indicated by the arrow, curves outwardly. If this is the case, then I have formed, or I have created what we call as convex mirror. So for convex mirrors, the reflecting surface curves outwardly, whereas the coated surface curves inwardly. So these are the key difference between concave and convex mirrors. Now the question is that why do we call concave mirrors converging? And why do we call convex divergent? We call them concave and convex, convergent and divergent respectively, due to the fact that for concave, when we incident parallel beam of light, parallel beam, numerous rays of light, 1, 2, 3. Mirrors generally reflect. Mirrors reflect light. So when you incident parallel beam, which is very close to a line known as the principal axis, will come to parts of the spherical mirror. This mirror has the ability to converge all parallel beam and bring them to a common point. So concave mirrors converge parallel beam of light. It is of this reason that concave mirror is also called converging mirror. Then for convex, when you incident the same parallel beam of light, this one would spread out, diverge parallel beam of light, so these are parallel beam. This one will diverge, and here the diverted rays, please, rays must be indicated with arrows, so reflected, reflected, reflected. Here incident, 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 and then the reflected. Now, when we trace the reflected beam or rays at the back of the mirror, when we retrace the reflected rays at the back of the mirror, the reflected rays appear to be diverted from a point behind the mirror. So the reflected beam appears to be diverged or from this point. And we'll talk about these points. Okay, so this is the reason why concave mirror known as converging, convex mirror also known as diverging. So you can be asked to, using ray diagram, explain why concave mirror is also known as converging mirror, and convex mirror also known as diverging mirror. This is what they expect of you. Yes, Elikem.
Sir, please, the ray in the middle, the convex mirror, will it reflect back on the same path?
When it's incident on the mirror at 90, it will reflect back. That is why you see the two arrows. So the moment you see the two arrows, it's an indication that the ray, incident ray, is hitting the mirror at 90. Elton, are you okay?
Yes.
Please, if you have any question, Frank.
Please, could you explain that again?
Which part?
the middle light ray
See,
reflected.
the rules of the game is that when for mirrors, when a ray of light, not only for mirrors, under reflection and refraction, when a ray of light incident on a mirror and the ray is perpendicularly to the mirror or the Sidel, can you please mute yourself, Sidel? So the moment the ray hits the mirror at 90, it will reflect along the same path. So if you see incident going to the mirror, reflection going back, then it means it is the incident ray is hitting on the mirror at 90. Shaki, quick one.
Sir, please, so are you saying that the convex mirrors, the rays, it causes the rays to diverge only when they hit the
No. What I'm saying is that for convex mirror, when you incident parallel beam of light, it will diverge it. It will diverge it. But when you see this, then it means the incident ray is hitting the mirror at 90, this one. So where we have an arrow here and here, then it means it is just hitting the mirror at 90. Okay. Please, did we discuss the uses of the spherical mirrors? Did we discuss the uses?
Yes, sir.
No, sir.
Hey, Jesaki, you were not here. Okay, one. Concave mirror or mirrors are used in reflector. They are used as reflectors in torchlights, headlamp, searchlights for security, searchlights, and then it is also used in car headlights lamps, searchlights and car headlights lamp. It is also used as shaving mirror. Then convex. Convex mirrors are used as one side view mirror. The side view mirror of cars. The head view. You see that mirror, which is at the head level of the driver. Genius.
Please, can you say concave mirrors are used for lenses with people with short-sightedness?
No, these are not mirrors. They are lenses. We'll come to lenses, okay? Are you okay?
Yes, sir.
Side view mirror of cars, head view mirror, and it is also used for security and surveillance. And surveillance purposes in supermarkets. These days, that is not common in supermarkets and shops. That is not common because these days we have CCTV camera. But in those days where CCTV isn't common, it is the concave, convex mirror that is used for security and then surveillance in shops. So when you enter the shop, you realize that a mirror is mounted at a corner of the shopping area. Its purpose is basically to catch, and yes, some supermarkets. So, and Frank, the issue is that if you can't afford CCTV, then you go for it. Okay, so it is mounted at the corner so that if you want to be fast, they can also be fast at you. Angela.
So please, my network was unstable, so I didn't hear anything you said about the convex mirrors.
Okay, so one of it is that it is used for, it is used as side view mirror of cars and also the head view mirror of cars. So the mirror that is used at the side of the gate, they are actually not plain mirrors. They are curved. Okay, so the surface, the reflecting surface actually curves outwardly. And it is also used for security purposes and for surveillance in supermarkets. But that's what I'm just saying, that these days, because of CCTV camera, it is not so common. Then it is also used for road safety along curvy road, used for road safety along curvy roads. So as you drive and then you get to curvy roads, you see these mirrors mounted so that when the driver gets to that part of the road, he can have the opportunity to have a clear view of his back. When you look through, you can have a clear view of your back in order to watch traffic and all that. So it is also mounted along curvy road for road safety purposes. Let's understand why we use convex mirror or divergent mirrors for these purposes, but not plain mirror and not concave mirrors. Now, if we pick the same size of all the three mirrors, let's begin with plain mirror, a smaller size. And then we try to picture or use ray diagram to create the image that will be formed when an object is just placed in front of all of them. This is plain mirror. So we are drawing rays to hit the extremes of the mirror. So a ray of light from the object hitting one extreme of the mirror. Mirrors reflect, so we expect this to reflect the incident light. So this is the reflection. Another ray from the object hitting the other extreme. Of course, it would also reflect This is the reflected ray. Now, an observer here this is an observer's eye, sees this image of the objects here within this range. Or the image of the object would appear here. So this is the field or angle of view to the observer. This is the field or angle of view. So field of view. This is a field, I can't write, field of view. Field or angle of view of the observer. Looking through. So this is a range within which the image can be seen. Let's also have the other mirrors, this time concave, of the same size. No, I can't use double. Of the same size as the plane mirror. And when an object is here, an object O placed at the same location. So let's have rays hitting the extremes. This will reflect, but it will reflect by converging rays. Another ray from the object hitting the extreme of the mirror so the reflected rays actually converge here. An observer looking through the mirror, this is reflected incidents, would actually see the image formed within this range. So for concave, this is the field of view. Now, the same aperture of convex. The same aperture. This aperture or size of the mirror is even large. Just small aperture. An object placed here. And let's see how this will form the image. So a ray of light hitting the extreme, this mirror diverges rays. So the reflected ray will be diverged. Another one, and will also be diverged. So incidents, reflected, and an observer here sees this image formed within this range. Of course, this becomes the image. So an observer here will see this image within this range. So when you compare all of them, there's the objects, there's the image. When you compare all the mirrors, concave, plane, and convex, which of them has a wider field of view? Class.
Convex.
Which of them has a wider field of view? Clearly, convex mirror. So, because of the wider or larger field or angle of view, it is for that reason that the convex mirror is used for side view mirrors, head view mirror, used for security and surveillance in supermarkets. Because if it is mounted within a shopping area or in the supermarket and somebody is viewing, whenever you get close, it will enable whoever is watching to have a larger view of the shopping area. So whoever wants to be smart on them can be seen compared to even plain mirror. So it is of this reason that convex mirror is used for these purposes. This is the advantage it has. The advantage it has over all the other mirrors. Are you okay? The other advantage it has, we'll discuss image formation, and you look at, or you see other advantages this one has over concave. As for plane mirrors, they will all give upright or erect images, but concave mirror will not always give you upright images. Sometimes the image will be inverted. Okay, so but this is the reason why a key advantage it has over all the other kinds of mirrors. A convex mirror has a wider or larger field of view. And so when you imagine when you are driving and you look through, it will give you the opportunity to have a better view of your back than plane mirror, than concave mirror. Gideon.
So, but with convex mirror, the image form is always inverted.
Not always inverted. We'll discuss image formation. So when we get there, we'll cross. Okay.
Okay.
All right. So let's quickly look at the parts of the spherical mirror. Parts of spherical mirror. Please, are you done writing and sketching?
No, please.
Okay, then hurry up.
No,
Frank, I will explain when we get there. We are here to treat that. When you finish, please draw my attention so I can pick it up from there.
Recording in progress.
Gideon.
So please, in the concave mirror,
Come again.
for the angle theta. So please, with the angle theta, what does theta represent? In the concave mirror.
Theta represents the field of the angle of view or the field of view.
Okay, sir. Please, thank you.
Please, if you have any question, don't hesitate to ask, okay? Can I continue? These days we have 30 minutes, so please, whoever is joining with the name Liverpool should identify his or herself. Very important. Or is it the Liverpool team? Whoever is joining with the name Liverpool, can you please identify yourself? All right, so let's continue with parts of the spherical mirror. I earlier said that the spherical mirror is part of the spherical ball. So part of the spherical mirror. So this one applies to both concave and convex. This is a sphere. So if I pick small section of the mirror, A, B, and then coat the back, I have formed concave mirror. This height or depth AB of the mirror is known as the aperture. Class, say it with me. Aperture.
Aperture.
Again.
Aperture.
Aperture. You must be practicing it, else the next time you say it in class, if you don't say it well, they will laugh at you. Aperture. It can even turn to your name. So the depth or the height, vertical height of the mirror is known as the aperture. So whether concave or convex, the aperture is the vertical height. So for convex, this is also the aperture. Now the center of the mirror itself, or the midpoint of the mirror, is known as the pole. So P is the pole, which is the center or midpoint of the mirror. The pole. Then you see the center of the whole sphere itself. The center of the whole sphere, out of which the mirror is carved. The center of the sphere which is also part of the spherical mirror, has a name. This is represented by the letter C. And so C is the center of curvature. Center of curvature. I note that the center of curvature is not the center of the mirror, but is the center of the whole sphere out of which the mirror is carved. Please, a minute to pick this call and get back to you, okay? So we have the center of curvature, which is the center of the sphere. Please, not the center of the mirror, but the center of the sphere. So when you draw a mirror, whether concave or convex, you must indicate the center of curvature. We'll be going deeper into it. So you AB is the aperture, then the middle or the midpoint of the mirror itself, which is the pole. Then you must indicate whether it's concave or convex by quoting one side of it. Then a line drawn through the center of curvature and also through the pole of the mirror has a specific name. So for concave, when I draw a line through the center of curvature, passing through the pole of the mirror, this line is known as the optical, the principal axis. So the principal axis is a line passing through the center of curvature and also through the pole of the mirror. So if this is the center of curvature of the mirror, this line through C through to P is what the line can actually be extensive. It can go, it can continue. So the line through C through P is what we call as the principal axis or the chief axis. So CP, let me indicate a continuous point O here. So in this case, CO, because CP has a particular name. CO is the principal, into brackets, chief axis. It's not CP, but CO. The line must continue from P. Okay. Now this distance, okay, before I talk about distance, there is also another point on the principal axis where rays that are close to the principal axis and also parallel to it would converge. So if the ray is close to the principal axis and also parallel to it, after reflection, it will, for concave mirror, it will converge on the principal axis. And note that for this to happen, the incident rays must be parallel and very close to the principal axis. The parallel rays shouldn't be so far from the principal axis. They must be close. And you understand why they must be close later. So when you are drawing this, you must do that carefully, considering the closeness of the parallel beam. Okay, so these are the reflected rays. They were all incident on a point represented by capital F. This point is known as the principal focus. F is the principal focus. Another name for this same point, capital F, is known as the focal point. Focal point. Please, are you following? So let's now define key terms. What is the focal point of a concave mirror? I'll also talk about the focal point of convex. How do we define the focal point of a concave mirror? Please, can somebody help? What is the focal point of a concave mirror? Anybody to just give a try? Saki.
This is where all the reflected lines meet.
All the where all the reflected lines meet. Nice try. More views. Or a final view. Okay, listen to my version. The focal point is a point on the principal axis where rays that are close and parallel to the principal axis actually converge. A point on the principal axis where rays that are close, the rays must be close and parallel to the principal axis actually converge. converge. There is the use of the adjective actually, because for concave mirror, the principal focus is real. Why is it real? So please write that as well. The principal axis, the principal focus or the focal point of a concave mirror is real. This is real because it's actually, when you incident reflected parallel beam, it would actually incident here. And it is for that reason that this point F occurs in front of the mirror. All points or locations which happen in front of the mirror is considered real. So for concave mirror, the principal focus is real. The center of curvature is also real. And this is the principle used in car headlight lamps. We have what we call reversibility of light. Light rays can be reversed. So you see, look at where the bulb of the car headlight lamp is. It is located at a particular spot within the mirror, the focal point, so that when you on the light, the rays will be thrown in that parallel manner. And when they are thrown in that parallel manner, the rays can be able to go far. That is why car headlight lamps can actually go very far. Okay, when you switch it on and then you bend the bulb at an angle, it would precisely be at F and the rays would go far. Equally, if you have rays coming in that parallel manner from afar, the moment it hits incident on the mirror, they will all be converged at F due to the principle of reversibility of light. Gideon, your hand is up. Okay. So a point on the principal axis where rays that are close and parallel to the principal axis actually converge. This point is the principal focus or the focal point of a concave mirror. Please, this is of a concave mirror. Now, what about the principal axis, the principal focus of a convex mirror? Gideon.
So we wanted to ask a question concerning the headlights of a car. So when you are out at night and then cars are coming towards your direction and you see their headlights, it's like you are seeing some rays moving in different directions. So what do you call that?
What I'm saying is that the rays must be direct to obey the principle of reversibility. The bulb must be located at a particular point. That is why cars are such that they can adjust. Okay, there's a knob which, when switched, would adjust the position of the bulb. The bulb can go down or come up. What the idea behind it is to decide whether you want a beam of light which is thrown parallel or at other angles. So when you see it from different directions, then that is the meaning. Meaning the bulb is not positioned at the principal focus, because if it's at the principal focus, it must come to you in that parallel manner. Okay. Let's look at the principal focus or the focal point of concave.
So please, can you go back to the previous slide so that I can take a shot?
Oh, but I'm recording. Okay. So please, these days we have 1 hour 30 minutes. So if you need to, if you were not fast in capturing something, please, the recording would come. Okay. So we can utilize our time properly. I beg you. Else we can't be doing more as we so want. So for a concave mirror, the reflecting surface curves outwardly. I want to explain this using the spherical ball as well. There's the center of the ball, center of curvature. So let's pick a small aperture, AB. So this is the aperture AB of the mirror. The center of the mirror, the pole is here. A line drawn through the center of curvature through to the pole is the principal axis. So if this is our center of the mirror, P, don't forget for convex mirror, the center of curvature is behind the mirror. So this is all locations or points that are behind the mirror are virtual. So clearly a convex mirror has a virtual center of curvature. It is not actually there. Now this one, let's extend the principal axis. If you incident parallel beam of light close and parallel to the principal axis, this mirror converges reflected rays. This one also converges reflected rays. But the reflected rays always appears to be, or the diverted or diverged rays always appears to be diverted from a point behind the mirror. So the reflection of this must always be traced to a point which is behind the mirror. This point where reflected rays appears to be reflected from is known as the principal focus. Angela.
Sir, please, I didn't get that. Please, could you come again?
Whoa.
Thank you.
So I'm just, for explanation's sake, I'm adding on to the incident rays. So incident, then reflected. Convex mirror has the nature of diverging reflected rays. Okay. But when you incident parallel beam or rays, they will be diverged. But the diverted rays or the diverged rays always appears to be diverted from a point behind the mirror. So yes, these are 1, 2, 3, 4 diverged or reflected rays. But the diverted or reflected rays always appears to be diverted from a common point behind the mirror. This point is the principal focus of it. Okay, this point where reflected rays appears to be reflected from or diverge from is the principal focus of convex mirror. So by its location, the convex, the principal focus F, or the focal point, focus F of a convex mirror is virtual. It's virtual. Why is it virtual? It is virtual because it's a point which occurs behind the mirror. Okay. Its principal focus and center of curvature of convex mirror are all virtual points. Are we okay? Saki.
So because the focal point of a concave mirror is in front
of, yes, in front of the mirror, and the center of curvature is also in front, it is real. In mirrors, when a point image is formed in front of the mirror, a point and image is formed in front of the mirror is real. Whenever a point or image is formed behind the mirror, is virtual. Please, are we okay? Class, are we fine? Hey, are you there? Nobody is talking.
Yes,
So,
please.
can somebody help me define the convex, the principal focus of a convex mirror? Can somebody help define or explain the convex, except convex, the principal focus or focal point of a convex mirror? Anybody? Before I call. Janelle, okay, Saki. Saki, go ahead.
Please, the focal point is where rays that are close and parallel to the principal actually diverge.
Okay, more views. Yes, another hand is up. Please go ahead. And Saki. Please, if your hand is up, go ahead. Gideon.
So please, the focal point.
The principal focus.
The principal has, sorry, the principal focus is where the rays that are close to the parallel and principal axis actually diverge.
Yo, Mate. Let me also come in. The principal focus of a convex mirror is a point on the principal axis where rays that are close and parallel to the principal axis appears to be diverted from. Anita, Ablina, Elitia, and the rest of you, these days I don't hear from you. I'm taking it again. The principal focus or focal point of a convex mirror is a point on the principal axis where rays that are close and parallel to the principal axis appears to be diverted from. Appears to be diverted from. And the phrase appears to be makes it virtual. It's not real, but it appears to be diverted from. All reflected rays appears to be reflected or diverted from that point, which is the principal focus. So when you are defining this, you must be very careful. Okay, you must be very clear which of the mirrors is being talked about here. The principal focus of a concave mirror is a point on the principal axis where rays that are parallel and close to the principal axis actually converge. The use of actually means that it's real. It really happens. And what about the principal focus of a convex mirror? It's a point on the principal axis where rays that are parallel and close to the principal axis appears to be diverted from. Okay, so that's the difference. So generally, if you are asked to define the principal focus of a curved or spherical mirror, define the principal focus of a curved or spherical mirror. Here, the question isn't specific as to whether it is concave or convex. So how then will you define it? Angela, how then will you define it if you are to explain or define?
So it will be, the focal point will be a point on the principal axis where rays that are close and parallel to the principal axis appear to be diverted from or actually converge.
Okay, not bad. More views. And I want this time let our ladies also talk. Okay, Mercy is here. I never knew Mercy does physics. Mercy, go ahead. Mercy, go ahead.
It is the distance between the principal focus and the center of curvature. The center.
Mercy, this is the principal focus of a curved mirror. We haven't been specific as whether it is concave or convex. So how would you define it? That's the question. Okay, for time's sake, let me also come in. So it is a point on the principal axis where rays that are parallel and close to the principal axis actually converge or appear to be diverted from. So here you must fuse the two. A point on the principal axis where rays that are close and parallel to the principal axis actually converge or appears to be diverted from. Okay. All right. Angela.
Sir, please, I have a question.
Go ahead.
Sir, please, does that mean that in a concave mirror, the image is formed in front of the mirror, not behind it?
Not all the time though, but in most cases, image is real for concave mirror. We will look at formation of images in both mirrors, but it is only in one situation where a concave mirror would form a virtual image. But in all other situations, the image is in front, real. Okay.
Thank you.
All right.
Okay, thank you.
Let's go back to our. So we've discussed the points, the pole, the principal focus, and then the center of curvature. Now the distance between the pole and the principal focus, the distance between the pole and the principal focus, this distance PF. Please, all measurements are taken from the pole. So the pole of the mirror is our reference point in terms of measurement. Okay, so the distance, so you can't say that the distance FP is PF because all measurements is taken from the pole. So the distance PF is given the name focal length. Focal length, represented by the letter small letter F. So small letter F is the distance between the pole and the principal focus, and capital letter F is the point, which is the principal focus or the focal point. Note the difference. Then the distance from the pole to the center of curvature, which is PC. PC is known as the radius of curvature. Radius of curvature. Represented by the letter R, small letter R. Other books also use capital letters. What is important is R. So the radius of curvature is the distance between the pole of the mirror and the center of curvature, whereas the focal length is the distance from the pole to the focal point or the principal focus of the mirror. By geometry, by the use of geometry, we can prove that radius of curvature R is equal to 2 times the focal length F. We can actually make this, we can prove it. So note that R is equal to 2F. So if you take a measurement of 5 centimeters from the pole to the principal focus, then the distance from the pole to the center of curvature must be equal to what? Plus, if F, small f is 5, what must be R? What must be R? Anybody? Come again. If F is 5, what must be R?
10.
10 centimeter. And if R is 10, what must be F? If R is
5.
10, what must be F? 5. Please note these things carefully. We'll be using it in image formation as well as mirror formula. Okay, is there any question? Please note that for concave mirror, F, principal focus is real, center of curvature is also real, because they all occur, they are all points which occur in front of the mirror. But for convex mirror, F and C are virtual because they occur behind the mirror. We just have a minute to end the lesson. If you have any question, ask. Is there any question? Ella.
My question is that curved mirrors.
Ella, speak up.
Yeah, please, I'm asking principles of.
Hey, Ella, your line is fading.
Hello, yeah, please, can you hear me?
Yes, it's better now.
Please, I'm saying that
Principles of what? Ella, write it. Send it to me. I'm finding it difficult to hear you completely. Okay, so forward it to me. Angela, ask your question.
Sir, please, can you give a real life example of a real image formed by a concave mirror?
Oh, it's just like, yes, we can, even the real life experience, just pick a brand new spoon. Okay, then look at a brand new spoon. The reflecting surface is the inner part which holds liquid, and the coated end is the part which, okay, when you look at yourself within a brand new spoon, you see an image of you, which is magnified. We'll look at characteristics of images formed by concave mirror. And so the brand new spoon the image formed by the brand new spoon is typically an example of the nature of image formed by this. Okay, so let's go through the principle, the nature of images formed, and you understand it very well when you use the brand new spoon I'm talking of. And we equally have curved mirrors. We have spherical mirrors. Tomorrow, I'll check if I can get a number of them from the lab and show it to you. All right.
Okay, sir.
All right.
But sir, can it be formed on a screen? Since real images are formed on a screen, can the image formed by a spoon?
Yes. For concave mirror, I told you it is only in one instance where the image is formed virtually. All other position is real, and it is formed on a screen. We have practicals to this, so you don't worry.
Okay, sir.
Frank, I'm saying that this is your question. We are here to treat it under formation of images in mirrors. So I'll address why the image in convex mirror is formed closer than they actually are. So I'll explain that during tomorrow's lesson. Okay. Ella.
Hello, sir.
It's better now.
Well, I've sent it though. But the question is, does the principles of the curved mirror also apply to that of the parabolic dish?
Yes. So you see what I was talking about, the headlight lamp of cars. When the bulb is positioned at the principal focus, the light will travel in that parallel manner. It is the same technology that is used by this multi-TV, multi-choice. You see the feed, okay? is connected at a particular position, so that when the rays is picked electromagnetic waves from external, when it hits the dish, okay, it can converge within the feed, so that the feed is, we have the cable connecting to the feed. So when all the rays converge at the feed, then it can be tapped by the wire which connects to the decoder in your home. So it is the same principle that is used by this dish and antennas. Is that okay?
Okay.
All right. Okay, so we'll continue our lesson tomorrow. Please, if you have any question, you can forward it to me so I explain to you. Until then, please do not forget to try the second question. Okay, that is your assignment for today. I'll re-forward it so that it will serve as a memory to all. All right, may the good Lord be with you. Take care. Please, I'll upload this video, but when you go to the page, please, if you haven't subscribed to my channel, do that for me. All right. Bye-bye.
Bye.